sampling. So we'll so sampling of a continuous time signal. This is the topic for today's lecture. This is chapter number 5 in Offenheim and Schaeffer book. Last time I explained a little bit about sampling, but sampling is really very critical once you are designing a digital signal processing system, because this is the input to your system. If you put garbage in, you get garbage out. I mean, there's hardly anything you can do if you don't appropriately sample here. And same is the case here. We have spent a lot of time struggling. If you make a mistake here or here, it's very difficult to fix. A mistake done while selecting a to D converter will really hurt you in your system. And same is the case if you don't appropriately select a D to A converter, that will also hurt you. So very important to understand the intricacies of sampling. And in this we say sampling means, from the chapter's perspective, it talks about continuous to discrete time converter. It says while learning sampling, let's not really worry about the quantization, though quantization has a big effect on the overall system. Quantization means how many bits will you get once you sample a signal. So number of bits per sample is important. But this book starts with saying ignore that. Assume that if this is a signal, then you can precisely record the value of the signal, which is obviously not possible. That requires infinite precision. You got to have levels, and levels will, if you have levels, a finite number of levels, then it may happen that once you sample, your sample is not appearing on any one of the levels. It is between two levels. So this is called quantization. Then you got to quantize. Either you say it is the lower value or the upper value. This is a quantization noise which is fed into the system. Okay, so you may live with 8-bit, like in videos you have 8-bit, maybe fine. You may have 12-bit, 10-bit, 14-bit. So more the number of bits, better it is. But sometimes you will not find high precision A to D converter, so you need to live with the low precision. But this is an important point which we will ignore initially, and we may come back to it at some point. Okay, so that's the reason the book says continuous to discrete. It assumes a way of exactly describing the signal. Okay, a value, finite, infinite, precision, convert it to digital, process it, and convert it back from digital to continuous. So this is the A to D conversion and D to A conversion. The process of sampling is modeled. To understand, the process is mathematically modeled to get really inside the sampling, that what is actually happening once you sample a signal. And this is how it is modeled. It says sampling is really like if you multiply a signal with a train of impulses. A signal with the train of impulses, what you get is a train of impulses altered by the magnitude of the signal at the location of the impulse. For example, if this is a signal and you multiply it with a train of impulses, means with an impulse here, an impulse with unit magnitude. So this is what you multiply. So you multiply these two signals, and this is in continuous domain. It's a model. It is in continuous domain, means that an impulse in continuous domain is delta of t. And this delta of t is unit impulse. It obeys certain characteristics. One of the characteristics of this impulse is that if you multiply a function f of t with an impulse delta of t minus t naught, okay? If you multiply an impulse with a function, an impulse is at t naught, because impulse is 0 everywhere other than t naught, so it'll make, once you multiply this with this, it will make this something multiplied by 0 is 0, so I'll remove that. Something multiplied by 0 is 0, and at the location of the impulse will change its magnitude to ft naught. So this is the magnitude of the function at time t naught, at the location of the impulse, and the impulse will remain as is. So multiplying this with this will eat up the function, and you will have an impulse with changed magnitude, and now the magnitude is equal to ft naught, where t naught is the value of the time axis, the time index at the location of the impulse. Yeah, this is just a theoretical model. We are not implementing it. We are saying this is just a theoretical model. I will say what happens actually, but this is not. It's a purely theoretical model to get into the maths of sampling. Right? Because you want to get to a point where you see samples, but it says let's try this model. Different books you will find different treatment of the sampling problem. Right? But this is a good enough treatment. It says multiply a train of impulses with a function. If you do that, you will get impulses, okay, where the magnitude of the impulse will be equal to the magnitude of the function at the location of the impulse, and the function will go away. You won't have any function. This is what you will get. If you multiply a train of impulses with a function, what you get is so this is your train of impulses. If you multiply this with this, you get the same impulses at every capital T. Amplitude of every impulse is equal to the value of the function at the location of the impulse. X n capital T is the index. Okay, so this is what in time domain, all we are saying here is that if you multiply a signal, this is your signal, with train of impulses at every 0t, 2t, minus t. So as a result, you have this is what you get. Okay, still at 0t, 2t, minus t, and dot 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 dot. Okay, so means that you get x if this is x of t. So here the amplitude is x of 0, here amplitude is x of capital T, here amplitude is x of 2t, here amplitude is x of minus t. Okay, and impulses are still there. So it says it is x of n capital T delta of t minus n capital T, and n goes from minus infinity to infinity will be your xi of t. Still an analog signal. Again, this is a mathematical model.
ये तो हम मैथमेटिकली डेवलप कर रहे हैं सर इस थ्योरी को, तो मेरा ख्याल है सर इसका पर्पस सर प्रैक्टिकली तो ये होता होगा कि वो बस उस सैम्पलिंग रेट के मुताबिक वहाँ से वो सैंपल सिलेक्ट करेगा और
नहीं, इसका पर्पस ये है, द पर्पस ऑफ गोइंग थ्रू दिस एक्सरसाइज इज टू डिफाइन रूल्स ऑन सैम्पलिंग. That how fast should you sample, what sampling does to your signal, it's just defining rules of sampling. That's why you are making a model and then saying, okay, this is what the model tells us. So we'll shortly find out why we are doing this. So this is what you get, xit. So you get impulses. It says, okay, what you do is you take a signal x of t multiplied with a train of impulses. Then what you get is a train of impulses, okay, with amplitude is the amplitude of the signal at the location of the impulses. Then it says now discretize, and discretization means you convert impulses to sequence converter, and that says now take away time, divide the time axis by capital T. Okay, divide the time axis by capital T. This will make it 1, 2, minus 1. Okay, and just record these values. So these are now digital impulses. This is what you do to get to this. So you take away time once you convert an impulse to a sequence converter. Now you have sequence of numbers. So we don't really see anything to appreciate the model at this point, right? We say, okay, what is the point? So here means that you are now this nt, so x of n is in fact, you can use k, you can use this, is x of k delta of n minus k. This is the digital part of it, that it is value of the function which you can kt or whatever, and digital impulses. So these are digital impulses. First is at index 0, then index 1, then index 2, then index 3. But again, you don't really see to appreciate this. So let's move forward. This is the mathematical model which says multiply it with the train of impulses. You have a train of impulses, convert it to sequence, you have a digital signal. So you go this, you multiply, you get this, and then you have, so this is what you are doing. A signal multiplied by this, you get this, still time in seconds, and then you divide it by capital T. Now time is no more there. These are indices now. Index 0, index 0, index 1, index 2, index 3, index 4, 5, 6, 7, 8. Now these are the indices. Okay. Now let's see another interpretation of this. And that is why the model is important. Another interpretation is that once you say you are multiplying x of t with pt of t. So this multiplication in time is convolution in frequency. Okay, we have learned in signal and system course that in time domain, if you multiply two signals, basically you multiply them in frequency domain. So convolution in time is multiplication in frequency. So that is what you use. Here is okay. G? PT is the train of impulses. The PT, T is train of impulses. This is the signal which is written as delta of T minus N, capital T, N goes from minus infinity to infinity, is this signal. Okay? An impulse everywhere. So train of impulses is the PT of T. Right. It says it is the convolution, multiplication is convolution, which is 1 over 2 pi x of j omega, convolution pt of j omega. Means you take Fourier transform of both the signals, then convolve them together and divide by 1 over 2 pi. This is the formula. Multiplication in time is convolution in frequency. Okay, that will help you to understand sampling, this relationship. How the Fourier transform of xt is a signal. All you need to make sure is that it is a band limited signal. Means you can only sample a band limited signal. So you need to make sure that it is curtailed to some maximum frequency. So there is nothing beyond a particular frequency in your signal. That is the way you can sample a signal. You cannot sample an infinite bandwidth signal, so got to be a band limited signal. So you can only sample a band limited signal. So this is the band of the signal going from minus omega max to omega max. Okay, this is the Fourier transform of a signal. Shape is not important. We are only saying it is a band limited signal. If it is a real signal, then it will be symmetric. The magnitude will be symmetrically placed like this. So this is if we assume that x of j omega is this. Okay. Now what is the Fourier transform of this? It is a train of impulses. This is 2 pi over capital T summation k goes from minus infinity to infinity sigma j omega minus k omega sampling, which is 2 pi over capital T. I can write it like that. So this is the Fourier transform of
band limited signal है, reality में सारे signal usually time unlimited
जी, but होता ये है कि
जब time unlimited हो तो फिर इसका मतलब है कि वो band limited नहीं हो
जी, but what really happens is that it is, we say it is, let's say minus 100 dB down, you know, so the signal basically mainly concentrates in these frequencies, and usually with every A to D converter you put a continuous domain analog filter. So you put an analog filter to make sure that your selected band, so unwanted band is down, right? So with every A to D converter you must put an analog filter to clean the spectrum, otherwise sampling will corrupt. No sampling will be perfect then if you don't clean your spectrum, and that's the reason with every A to D converter, if it is not already there, you have to place an analog filter to clean the spectrum. Make sure that you have only this. You may put some guard here and guard here, but this is a must, okay, because otherwise spectrum is never clean. So you need to make sure the spectrum is clean, and then you pass it through an A to D converter. So this is the Fourier transform of a train of impulses. So if I draw it, this thing, it is saying, if I draw both, it says that the Fourier transform of, so in time domain I have a signal x of t, any signal, this is my x of t, okay, and I am multiplying it a train of impulses 0 t 2 t minus t magnitude 1, okay, and this multiplication will result into this signal, which is a digital signal. This is what you get. In frequency domain we are saying this is a band limited signal. Okay, so xj omega is a band limited signal. I assume it is this, and it has a maximum frequency. Beyond this I can safely assume it is not there. I mean, if may be there, but very very small component of it. जी अच्छा मैं put कर देता हूँ. Okay, here is max, okay, this I am assuming that this is the spectrum of the signal is this. I need to convolve it with the Fourier transform of train of impulses is train of impulses we have just learned, and it is at 0, and the location of the impulse really depend on the sampling frequency. 2 into 2 pi over t, and it goes like this. It goes like, okay. So this is the Fourier transform of this is this, and the magnitude is 2 pi over t, and here with the formula comes 1 over 2 pi, so 2 pi cancels with 2 pi. So train of impulses is train of impulses, the Fourier transform. You need to remember this. Train of impulses is train of impulses. If they are closer in time, they'll be further, they will be apart in frequency domain because t is appearing in the denominator. Here it is called the time period. Here 2 pi by t is called the sampling frequency, whereas fs is 1 over t, we know this, okay, and omega, so 1 over t, f of s, omega of s, this is how they are related, 2 pi f of s. This is how they are related. Omega f of s is in hertz. Usually you find people quoting things in hertz, omega hertz or gigahertz, or but otherwise omega of s is in radians per second. So slightly there's a small difference between the two. It's just a scaling factor. Now if you convolve this with an impulse, a function convolved with an impulse, what do you get? Anybody? Like, G? An impulse goes away, and so if you multiply the function goes away and you are left with an impulse. If you convolve, the impulse goes away and you are left with the function at the location of the impulse. So a function f of t convolve with, this is a mathematical relationship, t minus t naught, whether in time domain or frequency. If you're convolving a function with an impulse, the answer is function will be delayed or will be shifted, will be copied at the location of the impulse. This is the relationship, right? It's a mathematical relationship, that impulse, and again it's all mathematical. So if you convolve this with this impulse, a copy of it will come here. It's linear because then you convolve this with this, a copy will also come here. Then you convolve this with this, a copy will come here. This with this, copy will come here. So you'll get several copies mathematically. This is what the math tells us, that you get several copies of the spectrum at the location of the impulse in frequency domain. So I can draw it like this. Here it says then a copy at two pi over t minus 2 pi over t, magnitude is 1 over t, and many copies. This is the math tells us, and this is the Fourier transform of an analog signal xi j omega. This is the signal where we were saying you have only impulses, right? It is this. Then we said in time domain you divide the x's by capital T to make it digital. Here you need to multiply the x's by capital T. You do the reverse to make it digital. So if you do that, you multiply it by capital T, T cancels out with T, T cancels out with T, T cancels out with T. So that operation is equivalent to this operation in frequency domain. So now this is a digital spectrum, which is x of exponential j omega. Okay, x of exponential j omega, and we know that the Fourier transform is periodic over 2 pi. So you're getting perfect mathematical relationship. X exponential j omega is this. But the important point here is that you need to make sure that you sample fast enough. So t should be close enough that 2 pi by t is far enough so that you get copies which are not overlapping. Okay? So you make sure that you are sampling fast enough, that 2 pi by t is far enough that you don't get overlap. So if I draw this neatly, all we are saying here is that this should not happen. This should not happen. This is overlapping. That your sampling frequency, this 2 pi over t and the half is pi by t, must be away. So this is this is pi by t and this is y max. So pi by t must be greater than g. Okay, you don't have any control on the signal spectrum because that is your input signal. You got to sample it. The only control you have is on capital T. That how fast should you sample? You cannot go and say I'll cut it down because I don't have fast enough A to D converter. That will corrupt your signal. So the thing in your hand is an appropriate A to D converter. You say I will use the higher speed A to D converter to capture the spectrum. People usually capture a lot of garbage. Okay, if you have a faster A to D converter, it is always better to capture a wider spectrum, then clean it up in digital domain instead of using analog filters. Okay, this is done a lot. That if you can spend money to get a wider spectrum, which is fine, and then digitally throw it away. Okay, we'll spend some time on it, but here it says that your This is 2 pi by t, where the copies are, you are making copies. This is pi over capital T, and we are saying that this pi over capital T must be away from omega max. Okay, must be away from omega x. It must be greater than omega x. If I multiply it by 2 and 2, just to make this sampling frequency, so I say 2 pi by capital T must be greater than twice the highest frequency. Okay, this gives us a rule. So the modeling is done to get to this rule. To get to this rule, which says your sampling frequency must be greater than twice the highest frequency. And this is what I explained last time while teaching sampling. I said, in time domain you can appreciate it more. Okay, in time domain you can appreciate it more, but in frequency domain this is the rule, that omega of s must be greater than twice the highest frequency. If you don't obey this, the signal will alias. What is aliasing? So maybe easy to see it here, that this is fine if you are sampling fast enough such that your 2 pi over t is greater than 2 omegas of max. You are safe. If not, then what will happen? You will alias, right? What is aliasing? Aliasing is that the part which is not obeying will go back and corrupt other frequencies as well. Not only that you will lose this part, this is one issue, that if you don't sample fast enough you will lose the high frequencies. That may be okay, but the problem is that that part will alias back and corrupt the same amount of frequencies in your signal. Okay? So it is better that if you are sampling slower, you first throw away this part using an analog filter. Okay? Throw this away and then sample at a lower rate, so that at least you don't corrupt this part. Okay? So what you get here is this. For example, if it is 4 kilohertz and you sample at 4 kilohertz, the highest frequency content is 4 kilohertz and you sample at 4 kilohertz. Okay, what will happen? So 4 kilohertz is this, and then you make a copy at 4 kilohertz. Every copy is at sampling frequency. So if you sample a 4 kilohertz bandwidth signal at 4 kilohertz, you will get nothing, all garbage. This will be all garbage. Okay, so this is the point, that it's very easy to at least draw this. All you have to do is, usually there are questions in the book which starts, and I want you to please practice them. जी twice हो सकते हैं, twice is fine. Yes, twice is fine. It usually says greater than equal to twice. Okay, so this is Y max. Let's say I say it is a 4 kilohertz signal, so it is omega max is 2 pi into 4000. Okay, this is how it is written. So 2 pi into 4000 is Y max. It's a 4 kilohertz signal. It is 2 pi into 4000 is in radians per second. And now I ask you to sample it at 10 kilohertz, for example. So sampling at 10 kilohertz means omega s is 2 pi into 10,000. Okay, so these are the steps you need to follow. You say, okay, then it is capital 1 over capital T is what? 10,000. 1 over capital T is 10,000. Okay? So the steps are that you make a copy of this, because if you follow all these steps, you say, okay, this is in frequency domain, and then you have train of impulses in frequency domain, and each impulse is appearing at 2 pi over capital T. So first appears here, the second appears at 2 pi into 10,000, the third appears 2 pi into 20,000, appears here 2 pi into 10,000 minus. So this is the step that you make this, and this magnitude is 2 pi over capital T. Now you convolve them and divide them with 2 pi over, remember, 2 pi by T. So this convolution will make a copy of the signal at location of these impulses. So if you draw this, you get a signal here, a signal here, a signal here. So at 0, at 2 pi into 10k, at 2 pi into 4k. That's what you get. And here you will get 1 over t. 1 over t is what? 10,000. The magnitude is 10,000. 1 over capital T, 2 pi, 2 pi. Okay? This is what you get. Now you divide the whole thing by 1 over t. Divide it, multiply it by capital T. Multiplication means you divide it by 10,000 divided by 10,000. For sure you will get 2 pi here, but this is important. What do you get here? So 4k into whatever. What do you get? 2 2 is the 4, 2 5 is the 10, 4 over 5, right? Is this what you get? So k se cancel ho gaya, 2 2 is the 4, 2 5 is the 10, 2 2 is the 4. So this is what you get, 4 over 5 pi, whatever it is. So this is now the digital part where this is 2 pi, this is this, whatever, and then you can write it as exponential omega. This is the spectrum, digital spectrum. So G?
2 pi
yeah, you will always get 2 pi here and here. Okay? You will always get 2 pi. But the important is that you need to know, follow the steps. Okay? So follow the steps to get to a digital spectrum. Okay, so the aliasing will happen if you don't sample fast enough. If I say, okay, sample at 6 kilohertz. If you sample this at 6 kilohertz, then what will happen? You sample this at 6 kilohertz. 1 over t is 6,000. So 6 kilohertz means that you now have an impulse here, an impulse here, an impulse here, 0, 2 pi into 6,000 minus 2 pi into 6,000. And this is all that is there, 2 pi over t and 1 over 2 pi, whatever. It was here 2 pi over capital T, and here it was 1 over 2 pi. 2 pi cancels out. But you now have a copy at 0 to 4. Then, so if this is 0, 2, 4, 6, then you have a copy here. Okay? Yeah, this is what you get. Okay? So this is the aliasing part. You will only get a signal from 0 to 2k will be correct. 2k going to 4k will be corrupted. Right? The axis is 2 pi into 2k, 2 pi into 4k. It will be corrupted. Why? Because, so this will be, this is what you get. If you don't sample fast enough, you are going to corrupt the 2k to 4k signal. So, and last time I showed you that if you don't sample fast enough the high frequency, if you don't sample fast enough and you are sampling slower, so this is whatever, you will not get what really, yeah, so I think it will be something like this. So it will be a slowly moving sinusoid. So that slowly moving sinusoid which is already there will be corrupted. This is aliasing, that if you don't sample fast enough, the slowly moving sinusoid, the fast moving sinusoid will be mapped to a slow moving sinusoid and will corrupt the signal. Interesting is what, if you don't have that slow moving sinusoid. This is very interesting. Like if I have a frequency like this, okay, and I don't have any slow moving, I can really sample it at any rate, this sinusoid will map to a slower frequency for sure. You will still get a sinusoid. It will be a slowly moving sinusoid. It won't be this, but it will be there. A slowly moving sinusoid. It will not corrupt anything if something is already there. Okay? This is really used a lot, and we have used it a lot. For example, in digital communication, usually your signal is far at some frequency. Let's say your signal is at 70 megahertz, and it is only a 4 megahertz signal. A 4 megahertz signal. Okay, so 2 mega here and 2 mega here. Now, what is the highest frequency? So, if you obey this rule, you need to sample it at what rate? 144 megahertz. Very difficult to find such a fast A to D converter, number one. Then processing 144 mega sample. Just imagine 144 mega samples means these many samples every second you have to process. You have to store, you have to process. If you do that, and this is very common, like 70 megahertz IF is very common. But I know actually the bandwidth is only 4 megahertz. If I, by force, if I alias this, what will happen? If I alias it, I know this will map to lower frequencies. I am only interested in this band. I need to bring this band down. If I don't really sample at the desired rate, I mean I by force alias it to use a low complexity A to D converter, and also to move it down the spectrum, because I have to move this down the spectrum. So I give you a simple example. For example, here is a signal which runs from 2 to 4 kilohertz. Okay, and maybe it has a negative part, 2 to 4 kilohertz. Now this requires me to sample it at 8. I sample it at 4. I say I'll not sample it at 8, I'll sample it at 4. So let's try to sample it at 4. What will happen? You know, if I sample it at 4, I make a copy of it at 0, then I make a copy of it at 4, I make a copy of it at -4, at 8 and -8 and like that. So I make copies. Okay? So let's make a copy of this at 0. A copy of this at 0 will be exactly like this. A copy of this at 0. Copy of whole thing at 0 will be this and this. So a copy at 0 is you go to away, make this, you go to on this side, make this. Let's do a copy at 4. How do you make a copy at 4? Go 2 on this side and 2 on the other side. So go to here, make a copy, go to away, make a copy. Okay, now do it for this. Again, 2 away, make a copy, 2 on this side, make a copy. See, there is no aliasing. There is no aliasing. Though you are not obeying Nyquist, but by playing with this, you can sample it at a slow rate using a low complexity, and you can move it down. This is good. You can move it down, and now you can filter it out. You say, I only need this much. And then you further bring it at the baseband. Usually we want to bring every signal to 0 frequency in communications, to keep bringing it down. This is a trick which is used. So if only you have the complex, usually we do this as well. You say, I'll make this I and Q, I'll make it complex. The complex means you have only, the spectrum is only on one side. If this is on one side, then you can bring it down by again doing some the aliasing. You can even bring it to 0. You can think to bring this whole thing to 0. Maybe if you sample at 2, I don't know what will happen. Sample at 2, so maybe you bring it at 0. So you always, this is called band pass sampling. Doing this is called band pass sampling, and this you do if your rest of the spectrum is clean. Otherwise you can't do it. Okay? This is only possible if your signal is only at 70 megahertz and then rest of the spectrum is clean. If rest of the spectrum is not clean, then obviously you cannot do it, because you will be aliasing. For example, if you have a signal here, okay, but there is some noise here. A signal is here, okay. So, and now you say I will not sample it at the highest. If you do it highest, you are safe. Then you can remove this noise digitally. So first you remove the noise and then bring it down. But if you say, okay, the noise is here, and you band pass sample it. Once you band pass sample is, remember you are going to get a copy here and a copy here, which I just did. So there was already noise here. We call this out of band noise. It's the noise from the other bands. It is there. If that out of band noise is there, it's going to corrupt your signal, because now once you sample it, once you filter it out, there will be noise in your desired signals. It's very trickier to play, to do band pass sampling. Trickier in a sense, you really need to make sure that your out of band noise is no more there. But coming back to sampling, what I want you to really know is this. Ji? What if
far apart, दूसरा सिग्नल जैसा आता, इसका disadvantage क्या है?
There is no disadvantage of this, but the issue is, if you look at a spectrum, okay, the spectrum is very busy. If you look at spectrum, for example, just maybe go to frequency allocation board and look at the entire spectrum. What is happening in the spectrum, starting from 0? You know, there are these AM radios, then there are these FM radios, okay, then there are the army band, 400 megahertz around, then there is this 900 megahertz band, okay, which is for this mobile phones. So keep going down, the spectrum is very busy, very expansive. This piece of spectrum is very expansive. So is this piece of spectrum is also expansive. You really, to get few megahertz, you really pay a lot. No, you don't. No, you use it. You put some guard band there. Okay? You have to put some guards. Then you are wasting. That's why there is now, if you know, there is a spectrum sensing technique. Okay, very spectrum sensing technique. People are very actively working in this area. Currently, these spectrums are fixed. They are allocated. If you want a bandwidth, you need to go pay a price. And usually people pay a price, then don't use the spectrum. So, though you may find several people who have paid, who have a license for an FM radio, but they don't have an FM radio. They just buy it and they're just keeping it for time. Similarly, you may find several regions in the spectrum which are not busy, which are just localized. Maybe Army has this band, but Army is not using it. Especially 2.4 gigahertz band, it's called ISM band. This is free to use. You don't have to pay. Okay, you can, because the 802.11 works on this band. So they have allocated part of the band which is free for everyone. You can just design things around this band, but then it is very crowded, because all medical equipment works in this band, your cordless phone works in this band, your 802.11 works in this band. So wherever you have ISM band, that is expansive. Now in the spectrum sensing, what they do is they sense the spectrum which is not being used. Then they have this dynamic allocation technique where they go to the FAB, frequency allocation board of a country, and ask for a dynamic license, that we want to use this license or this band for this much time, and they pay. Right? But yes, to answer your question, yes, there are gaps and the spectrum is not. But what I really wanted to point out is, though at 9 and 70 megahertz, you may think rest of the band is clean. No, it is not. You know, the band is not clean. You have to clean the band before you process it in analog domain, because the band is occupied throughout. So in analog domain, you keep cleaning the band and bring what is your signal of interest. Only you leave that and rest, throw everything away. जी
बैंड पास सैंपलिंग सर, ये मेरे ख्याल में सिर्फ डाउन करने के लिए सर यूज
नहीं, you are using a slower A to D converter. You are processing less number of samples. Several reasons that you use it. ठीक है. अच्छा, coming back to the lecture, I said this is what I explained.
इस नंबर ले रही तो क्वालिटी पे तो बहुत फर्क पड़ेगा
जी,
क्वालिटी पे तो बहुत फर्क पड़ेगा
किस चीज का?
क्वालिटी पे परसिवली कोई नहीं एज्यूम करिए ऑडियो सिग्नल जो लिस्ट नंबर ऑफ सैंपल दे रहे हैं
Listen, no, it won't. You know, the issue is the actual band. For example, take the example of voice. So voice only really requires maximum 0 to 8 kilohertz, maximum, usually 0 to 4 kilohertz. Okay. So on your mobile phone, once you are talking, you are only consuming an 8 kilohertz band. Okay, this is the entire band you are consuming. But in order to use a spectrum, you have to move it up. Okay, you have to move it up to transmit, and that requires licensing and all those issues. That is the price you pay. So you say, okay, this is voice, is AM radio, for example, or FM radio, and now you need to transmit it at 99.9 FM. And 99.9 FM in 99.9 megahertz. Actual voice is only this, which requires how many, what is the sampling rate? Just say 16 kilo samples per second. So this voice only requires 16 kilo samples per second. But just to take it from here to here in digital domain requires 200 mega samples per second. Just taking this voice from voice to a band requires a lot more samples. Okay, so you are not really, you are still having more than 16 kilo samples per second, but not 200 mega samples per second. So this is the trick, that actually you don't require so many samples. And this is what we will spend more time on learning, that you do that and then you keep throwing away samples, because ultimately you want to come down to this, and this is what you actually play in the speaker. Only 16,000 samples every second. So once a signal hits your antenna, you got to sample at a very, very high rate, because it's a high frequency signal. At least 200, as I am saying, approximately 200 mega samples. And then throughout your system, and digitally you have to bring it down to this. And at the transmitter you take this and digitally bring it up to this to actually transmit, if you want to do it digitally. So you are not really losing anything. But coming back to this slide, we said you assume that there is a maximum frequency and there is nothing beyond this maximum frequency in your signal. If there is, you clean it out in analog domain. Then we said the sampling is really making copies of the spectrum xc, j, omega at every omega of s. And this is the mathematical interpretation, that you are making copies of the spectrum at every sampling, omega s, 2 omega s, minus omega s, minus 2 omega s. And from here you know that this is half the sampling frequency, and this point must be away from this point. This is what we just concluded, and for that, if you make that sure, it will result into the sampling theorem, that your highest frequency must be, your sampling frequency must be twice the highest frequency, and if you don't obey that, there will be aliasing, so it will be corrupting part of the spectrum. So this you need to make sure that you are not doing that. This I have already explained, that this is a train of impulses in frequency, and this is a train of impulses, a Fourier transform of train of impulses, and 1 over 2 pi you are convolving these. Once you convolve these, you make copies of x at every 2 pi k over capital T. Okay. This is in time domain, x of nt delta n minus nt, every location of the impulse, the magnitude is tailored according to that, and this is in frequency domain, that if you take Fourier transform of this is what you get, x or a Fourier transform of this, the Fourier transform of delta n minus nt is exponential minus j omega nt. So there is yet another way of looking at the expression. There's a lot of math in this section, but all I want you to remember is few things. And those are that once you are sampling, the only thing I want you to remember out of all this math is, once you are sampling, just remember the location of the sampling and make copies of the spectrum. Blindly make copies of the spectrum there. Usually I give questions in the exam where I will give you the spectrum. For example, I say this is the spectrum. Okay, and I ask you to sample it at, for example, this is 2 and 4, sample it at 2. And all you have to remember is, okay, you make copy of this at 0, then you make copy of it at 2, then copy of it at -2. And one way of doing it is actually draw this on a tracing paper. Okay, then make 0, 2, 4 and actually place the tracing paper, make a copy, move the tracing paper at 2, again make a copy, move the tracing paper at -2, again make a copy to make sure that you're not missing anything. So copying means copying the whole thing. If I give you, for example, a funny looking signal like this, something like this, and I ask you to sample it at some rate, so you have to make the copy of the whole thing at every omega of s. That is all you need to remember from this part, that take this, if you have to copy it on a tracing paper, then take it on every omega of s and make copies and find out if there is aliasing, if there is something which is, for example, if this is a clean band, you will find out that if you sample it at 4, something will start appearing here and here. If you sample it at 2, something else might happen, but that is something you need to remember. But the mathematical interpretation is, we have seen, is just this, that once you do this, you are making copies of the spectrum at every 2 pi k over capital T. So this is the math. This, and if you take Fourier transform of this, you really get what is our discrete Fourier transform. Because if you take Fourier transform of this, x and capital T is constant, and Fourier transform of delta of n minus nt is exponential minus j omega nt. And this omega into t, and this is the formula, is small omega. If you multiply omega, so omega, capital omega into t is small omega. This is the relationship between continuous frequency domain, continuous domain frequency, and discrete domain frequency. For example, what is sampling rate? 2 pi over capital T. T cancels out. This is the digital frequency, sampling frequency. A discrete time sampling frequency is always at what? Always at 2 pi. Discrete time sampling is always at 2 pi minus 2 pi, 4 pi minus 4 pi. So this is what is done here and shown here. Now let me just recap what we have done here. We are saying that in while learning about the continuous to discrete time conversion, you remember, you take x of t, you take train of impulses, you multiply them together, you get an xi of t, then you convert these impulses to sequence, and that will give you x of n. This is a digital signal. Then I said in time domain this is a signal, in time domain this is a train of impulses, and here what you get is the same signal but tailored by a train of impulses. This is in time domain, all in time domain. And once you get to this point here, you have same thing but now digital signal. And these are just indices, and this is x of n. So we need to remember this. These are the steps. Okay, in time domain, a signal multiplied by train of impulses, you get this, then digitize, you get this. This is the mathematical model of the sampling process in time domain, but you really don't get any insight into this. It's not very helpful to understand what is happening. So that's why you take this in frequency domain. In frequency domain, this signal is band limited. You say, okay, this is band limited signal, 0 to omega max. The train of impulses is a train of impulses, but now at at every omega of s. You can call this omega of s, which is 2 pi over capital T, and the magnitude is 2 pi over capital T. So multiplication is convolution, 1 over 2 pi. So what you get here in frequency domain is copies. Okay, 0, omega s, minus omega s, and 1 over t. And then omega s is 2 pi over capital T. And once you come here, what do you get? Same thing, 1 over t, only now you have 0 here and 2 pi here and minus 2 pi. So this is what all you need to remember in this part. And mathematically we have seen that it makes sense. Now comes the DSP. Let's say DSP does nothing. It says, I just want to show you that you can recreate that signal. So it does nothing, but now pass it to a D to A converter, a discrete to continuous time converter. For that we say you follow the reverse step. Impulse to sequence, what you did was you said multiplied by capital T. Now you do the reverse. You say first, so I'm not doing any DSP on it. I say okay, convert the sequence to impulse. And what do you think we need to do for this? Put only the time back. Put the t back. And where to divide? So say let's put the time back. Put the time back. 2 pi over t minus 2 pi over t. Okay, so time is back. So now you are actually playing it on a D to A converter. So once you put first sample, then you put after capital T, you put second sample, after capital T, you put third sample. So now you are actually throwing samples onto a sequence to impulse converter, which is every capital T you are throwing a sample. And in time domain again, from this you are going this, right? So whatever is the signal, you are actually putting time back into the signal. Again you are coming to YIT, so to say. If that was XIT, YIT. Now, okay, this is fine. Then what do you do? Now you have copies of the spectrum. Literally what you do is you put it through a low pass filter. And this is all you do to convert a signal from discrete domain to continuous domain, that you pass it through a low pass filter with gain capital T, because T will cancel out with this T, will give you gain 1. And with cutoff frequency always at pi over T and minus pi over T. Okay, always. Half the sampling frequency. Because you want to throw away these redundant spectrum. At least theoretically it looks like that you will get exact spectrum back. No loss of information. Going from here to here you will not lose any information. At least in frequency domain we see this. Though while sampling you throw away a lot of information in time, as this is your signal. Once you sample, all the information happening in between two samples, you are throwing this away, at least in time domain. In time domain you are throwing away this information, but the process tells us, if you look at this process in frequency domain, that you exactly what you sample, you get exactly that signal back. So somehow the information which you threw away can be regenerated. So it is difficult to see that regeneration in frequency domain. But if you look at the process in time domain, you will able to see that, okay, this is the way the information is regenerated. Okay, so now there we went from time domain to frequency domain to understand the sampling theorem, which says that sampling which is also called Nyquist sampling criteria, that you got to sample at twice the maximum frequency. Here, in order to understand the reconstruction process, you need to go from frequency domain to time domain. So what do you get in time domain? So here we are saying, while going back from discrete to continuous, you first convert sequence to impulse, then pass your signal to a low pass filter with cutoff frequency pi by t, gain t, and this will return you the reconstructed t, which will be exactly equal to x of t, at least theoretically. Right? So passing through this in continuous domain, a low pass filter is multiplication in frequency, which is very trivial to visualize, but convolution in time. Right? So it means what I get here, which is, let's say if I call this y of t, get convolved with the Fourier transform of the reconstruction filter. Let me call this HR of t. So this is the reconstruction filter. So this is what we are doing, starting with a continuous signal, multiplying with the train of impulses, getting a train of impulses but in the shape of the signal, putting impulses to sequence, taking the time away, then sequence to impulses, putting the time back, then passing it through a low pass filter, and we get the signal back. And now we want to see this in what happens in time domain, how we get that back. And I also practically is also possible, almost you get the signal back.
सैम्पलिंग टाइम पे ले रहे थे तो
जी जी, I'll tell you how, because I'll tell you how you get the signal back. ठीक है? Let me show you that. And that is the reason people use signal processing everywhere. So now we are saying, okay, this is the process of reconstruction. You throw the time back. Throw the time back means dividing by t. Then you pass it through a reconstruction filter with cutoff frequency pi by t minus pi by t and magnitude capital T. This will eat up all the copies and will get you this. The signal, the original signal from where you started. So this is the process. You go from sequence to impulse, and then the reconstruction filter will give you the reconstructed signal. And also please remember the Nyquist sampling theorem, which says that you can reconstruct a signal exactly as what you sampled if you obey this criteria, and which says that your sampling frequency must be greater than or equal to twice the highest frequency content in the signal. Only then you can reconstruct exactly. Okay? And still we need to see how you reconstruct exactly. So this is the reconstruction filter in time domain. It is a sink. Okay? Up now think about this sink, which is sine pi by capital T into T, pi by capital T into T. Now we are saying you have a signal, only these things are there. Okay? These are the things which are there, and you need to convolve it with a low pass filter, and low pass filter is a sink, so you need to convolve it with a sink. So I just told you, if you convolve an impulse with a sink, what happens with any function? You make copy of the function at the location of the impulse, and impulse goes away. Right? So the impulse goes away. The sink is in a manner that it will always pass, the zero will pass from here. Yes, it will be like something like that. Okay? Now to convolve this with a sink again, what will happen? The impulse will go away. You will have, which is passing through. So at every capital T, there is only guaranteed that there is only one signal which is non-zero. Rest all the signals which pass through zeros. While you make a copy here, what will happen? So everywhere once you make a copy, what do you guess? That between two samples, though you exactly generate these samples, so you already knew the information here, so you exactly generate these values, and the intermediate values, the values which you threw away, will be interpolated, and theoretically infinite many sinks will contribute to regenerate the values, these values. Okay, so infinite many sinks, you are just making copy, and infinite many things will contribute. I'll show you a MATLAB simulation as well, an interesting simulation which tells you how the reconstruction is done. But this is, remember, this thing always passes through T, 2T, 3T by virtue of its cutoff at pi over capital T. By virtue of its cutoff at pi over capital T, its time domain is h r of t sine pi by capital T into T over pi by capital T into T. So this is the inverse Fourier transform of this function, and we are saying you make copies of it at every, so this is the sink, and this is the concept. Okay, these are the impulses, and at the location of impulse you make a sink. At location of this you make a sink, at location of this you make a sink, but then between these two there are so many sinks, and they will recreate the value. Exactly, they will recreate the value of the signal. Okay, so this is again shown for a sinusoid, that the sinusoid is recreated. जी मैं अभी आपको दिखाता हूँ. Okay, let me show you a MATLAB simulation for this as well, for you to understand it. Okay. These all are demos, but let me first sampling demos, but I'll run them one by one, but first let me run the demo. I think it is here. Yeah, okay, let me first complete what we were running. Okay, okay, look at this now. These are the samples. Okay? Now at location of every sample you remove the sample and make a sink. Yeah, that's what we are saying reconstruction is. That location of every sample you make a sink. Okay? So this is the sink which you make here. This is the sink. Okay? Then for this you make another sink, and you keep adding those sinks, and I'm showing, so all the sinks are shown here and their cumulative effect is shown here. So I'm adding all of them together and showing that here. Okay? Remember, wherever now every other sink will pass through 0 here until you get a sink for this particular sample, only that sink will have non-zero value, which is exactly equal to the value of the sample. Okay, but then in between this you have a lot many sinks which are just adding up to give you shape of the signal. Okay, so look at this. So you keep running this. So this, now that this sink, okay, so you are reconstructing on left hand side. Okay. This sink, and this again all theoretical. This sink, those are all the sinks making up the signal. Okay. So this is how you reconstruct by, it's really interpolation is happening, but this is called an ideal interpolation. A sink is an ideal interpolator. But obviously a sink is not possible in that sense. So you have to pass it through a low pass filter, which will in analog domain. Okay, pass it through a low pass filter, it'll be something like this, and it will help you to reconstruct whatever you have thrown away. So now the blue signal is no more there. What you have is the signal. Right. So this is the reconstruction process. In reconstruction process, again, all you have to do is every location of the sample copy a sink, and sink must pass through zeros at the location of other samples, so that it should not corrupt the value which you already have. You already have this value. This is the only value you have. You don't want to corrupt this value, but you want to regenerate rest of the values. So the filter is designed in a manner that this value is retained. This value is retained, this value, this. So these values are retained and rest you recreate. Right? So this is the sampling process. And this is shown in, here as well. So to put them together, this is what we have learned today, that the model, again it is the model. Usually in reality you must have learned about a sample and hold circuit. It's sample and hold, sample and hold. Then you pass it through a smoother. Okay, so here you pass it through a sample and hold circuit, which will make you throw a value, it will maintain the voltage level to the same value. Then you throw the next sample, again it will maintain the value to the same. So this is what a sample and hold does. And then you pass it through a smoother, and smoother will smooth this out and recreate the signal for you. Actually this is how it happens, but theoretically we have seen that by this process kind of you can reconstruct. But the mathematical model says take a signal multiplied with a train of impulses, you get a train of impulses, convert the impulses to a sequence, you get a digital signal. In the reconstruction you take a digital signal, bring the time back by converting a sequence to impulse, and then what you have is pass it through a reconstruction filter. Passing through a reconstruction filter in time means keep making copies of the sink. That's it. It will recreate your signal. So to put the two things together, this is what we have learned. And I'll not start this, but this is the remember I was talking to you about the out of band noise will corrupt. If you don't make sure that your spectrum is clean and there is some noise which is coming from the analog part. So analog parts are not that perfect. So they have not cleaned the other channel noise. Okay? So then that corruption will appear in your signal as well. Once you sample them and don't sample them at an appropriate rate, you assume this is the highest frequency content. If you assume this is the highest frequency content, you sample it at 2B. Sampling at 2B will do what? Will make copy of the whole thing here. And copy of the whole thing will make all the things which you see appearing in your spectrum. This is what you need to clean. Okay? So what you need to clean two ways. Either you use perfect analog circuitry. One. The other is you say, I know there will be, no matter what I do, there will be out of band noise. So I will cater for all the out of band noise. Let's say here it is only 2 megahertz video, a 2 megahertz video. You say, I know, no matter what I do, I am going to have things till 6 megahertz. But it does not have perfect cutoff and whatever the analog circuitry. You say, okay, I don't mind sampling it at 12 megahertz. Okay, if you sample it at 12 megahertz, otherwise you would have sampled it at 4 megahertz. So what is the difference? Difference is 3 times. 3 times more cost basically. Right? There's a 3 times more complexity and cost. But do you really need 12 mega samples? Obviously not. What you do is in all these systems, and that will be the topic of our next lecture, that you say, okay, 12 megahertz fine, I don't mind, because I know there is some out of band noise which I cannot clean. So I will sample and I'll bring this noise in the spectrum digitally, and then I'll digitally clean it. So very first thing you do is you pass it through a very good digital filter. Okay, pass it through very good digital filter, and once you do that, what will happen? This will go away, this will go away. Okay, once this goes away, then what is the logical thing you should do? Then you throw away samples. You say, I need not to have 12 million samples every second now, because I know now I don't have the outer band. I have cleaned the noise digitally. So from here you go to here. So you throw away every 2 samples or whatever. Okay, every 2 samples, every 3 samples. So keep 1, throw 3, keep 1, throw 3. If you do that, you again get to 4 megahertz. So you never keep more than what is required in communication, in video, image, or whatever processing you are doing. But even in video or images, I'll show you example of images, I'll show you examples of digital signals. But the important is that you never keep more than what is required. Never. You will always have something which is not yours. So that is how you start. So there is something which is not yours, you bring it in, you throw it away, and then you say, now I also throw the samples. Because my highest frequency sinusoid is having more number of samples than what is required. And even 2 are more than enough. I know even if I have 2, I can perfectly reconstruct this sinusoid. So that is the game. You say, I know I can perfectly reconstruct the sinusoid, so why to waste my number of samples? But here it tells you that there is the out of band noise corrupting this, and out of band noise corrupting this is, you say, okay, no problem. Either I clean it up in analog domain, or I clean it up in digital domain. And once I clean it up, and then I can sample it at a lower rate. So this is what you do. And this is about the band pass sampling, which I have covered. That you have, further apart, but the spectrum is clean. There is no out of band noise. There is absolutely no reason for you to sample it at very high rate. You know the band, you sample it at a very low rate, and there are ways of knowing that. The formulas will cover it in the next lecture. And then you will have several copies here, copies everywhere. Okay, you will get lot of copies, because once you alias, it depends how much you alias. For example, if I give you a question, and we'll end here, I'll give you a question, I say, okay, 2, and this is an interesting question, I say not 2, I say it is 10 to 12. I say it is minus 10 to 12. I say this is your signal, and sample it at 4 kilohertz. What do? You first copy it at 0. What do you get once you copy it at 0? Same thing. But what do you get once you copy it at 4? And what do you get once you copy it at 8? Obviously, remember. And what do you get once you copy it at 12? So we are going to get lot of things here. And similarly, what do you get once you copy it at minus 4, minus 8, and minus 12? Okay. So again, a lot of things will happen. So the best way is you draw it to scale. Okay, plot it on a tracing paper, and then make copies, so that you know what is happening. And also remember, another important thing, also remember that I say that you are sampling at 4 means this is 2 pi. this is minus 2 pi. So digitally, you must get whatever you get at minus pi to pi or 0 to 2 pi, you will be getting replicas of it everywhere. You will be getting replicas of it. So 4 sampling at 4 means that this is your spectrum of interest, 0 to 4, that's it. Okay, rest are just making sure that you are getting the same thing again and again. So, but the only way to do this is, and now the interesting point is, how should I figure out the minimum sampling frequency which will give me this somewhere here without any aliasing. Okay, so we'll see what that is. So you need to figure that out, because you want to bring it down. Spectrum is clean, there is no point in sampling it at 24. Okay, so you do that. So we'll next time. So class is on Friday 6 to 9.